Hi everybody, and welcome back to part 7 of the Bravo project. So after part 6, I actually have posted 2 new videos. The first one being about the release of a new kit for Bravo project. The kit for the project is available at 8bitkits.com. So for those of you that are interested, I put the link in the description and you can check it out. The second video was about some tips and tricks in regard to soldering the project, and that one is also quite important if you actually decided to build a project. I highly recommend that you check that video out. It's going to help a lot in building the project. Now, with those videos out of the way, we are back on track to focus on our ALU. And now, if you remember from part 6 of the project, or video number 6, we actually built this PCB and we went through testing of our A and B registers. In this video, we'll be focusing on our ALU. So we're going to have a look at the logic behind the circuit, and then we're going to go ahead and test it. All right, so with that, let's get started. All right, so let's have a look at the circuit behind our ALU. As I mentioned before, our ALU is actually an 8-bit binary adder, which is made out of 274 HC283 chips. Each chip is a 4-bit binary adder with 2 sets of inputs, A side and B side. And what it does is basically just adding those inputs line by line and putting the results on the output lines. So that means that it's basically adding A0 to B0, A1 to B1, and so on, and the results will be put on the output lines. So if you have noticed here, each of those chips are actually a 4-bit binary adder. So in order to make an 8-bit binary adder out of these chips, we are cascading those chips together using the carry out and the carry in pins on each of those chips. So meaning that the carry out of the chip on the right hand side is actually going to the carry in pin on the chip on the left hand side. So this way we are basically combining those two chips together so that we come up with an 8-bit binary adder. Now first let's have a look at the output side. So if you have noticed, the outputs of those chips are actually going to a transceiver. I guess we have talked about that chip in the previous videos. This is basically a transceiver with 8 lines on the input side and 8 lines on the output side. And here, as you can see, the output of our ALU is actually coming to the B side, and the bus is connected to the A side. Oh, we have a pin here, which is pin number 1, which actually dictates the direction of data. And since the direction of data is always from B side to the A side in this specific circuit, then we are tying this pin to ground. Now, the other pin is pin number 19 here, which is connected to our sigma out, or I guess by convention we call it EO signal, which basically helps us to control when we want that data to be put back on the bus. So when the data coming from the ALU, it's going to be stored in our transceiver, and when we needed to actually put that data back on the bus, we just need to bring the E out or sigma out line low, and that's going to take care of it. All right, so I guess the output side is quite simple. Now let's have a look at the input side. So the input side, as I mentioned before, has 2 sections, right? The A and B. And if you noticed, the A lines actually come directly from our A register. However, the B lines seems to be going through a circuit before coming to our 4-bit binary adders. And there is a reason for that. And this actually goes back to the fact that what type of operation we want to do in our ALU. So by default, as I mentioned, this is actually an 8-bit binary adder. That means that in a normal situation, it only adds the values from A lines to the B lines. It will not be able to do any other arithmetic operation, right? However, I guess we would need probably subtraction, multiplications, and divisions, and so on. But if you think about it, if we could actually implement only addition and subtraction, we probably could come up with some sort of operation that we could do, let's say multiplication and division and so on. So the two base arithmetic operations that we need in any ALU is basically the addition and subtraction. Now, the addition part has been already taken care of, right? This is a binary adder. So the only thing that we need to resolve here is basically the subtraction part, how we could subtract two numbers from each other. And if you think about it, that could be done actually by simply making the b side a negative number. So let's say that if you could somehow make b a negative number before coming to our 4-bit binary adder, then by adding a plus minus b, essentially what we are doing is doing a minus b, and that way we could do a subtraction, right? So therefore we need to somehow convert the b value to a negative value when we want to do the subtraction. And this is done using a concept of 2's complements. So if you are familiar with the concept of 2's complement and how you could actually convert a binary number to a negative binary number, I guess you could just continue here. Otherwise, if you're not familiar with those concepts, I would highly recommend to watch a video from Ben Eder, which covers this topic in details. So I put a link to his video in the description. You probably would need to check that out before continuing here. So in order to actually calculate a 2's complement, aka a negative value for a binary number, you actually have to do two steps, right? In the first step, you're flipping all the bits and that original value, and on the next step, you'll be adding a 1 to the whole number. So this has been actually implemented here using two signals. The first signal is ES, or what we call it the subtract signal, and the other signal is called the carry signal, which you could see here on the right hand side. So let's first focus on the first step, which is actually about flipping the original values. Now, in a normal situation, when we are doing only addition, we keep that ES, or the subtract signal, low, obviously, because this is only used for subtraction purposes. Now, when the signal is low, as you can see, all the pins that here are tied together and actually are connected to that signal are going to one input on these XOR gates, or exclusive OR gates, right? And if you may know, the exclusive OR output will be 0 if both of the inputs are 0, or if both of the inputs are 1. Otherwise, it will depend on the input side. So in a normal situation, because one of those inputs is always low, essentially what will happen is that we are just pass-throughing the original value of B lines to the output. So we basically are not doing anything. We're just putting the B value on the output side as is in its original form. However, if we change that ES signal to high, then what we're doing here is that we are inverting those signals, meaning that if B0 is 0, there will be 1 on the output, and if B0 is 1, there will be 0 on the output. And that's all we need really here. We need to flip those bits, right? So this is the first step in calculating a 2's complement. Now, the next step is actually to add a 1 to the whole value, and that is done through that carry in signal that is connected to the first chip on the right hand side. So in summary, if we want to do an addition in this circuit, we just keep the ES and EC signals low, and basically what we get is that original value of B and the A is coming directly from A register. Therefore, our binary adder just add these two numbers together and put it on the output line. However, when we want to do the subtraction, we bring both ES and EC lines high, and that basically causes the B lines to be flipped, and of course EC is going to add 1 to the whole number, and therefore we are actually putting out the negative B on this circuit before it's coming to the ALU, and therefore we have a positive A, which is added to a negative b, and therefore we are doing a subtraction here. And that's really all about the addition and subtraction in our circuit. I hope that it is clear so far, because we're going to go ahead and look at a couple of more things here, which are called our flags. So we're actually dealing with three different types of flags in our ALU. Now, remember that flags are only outputs, meaning that we never set the flags manually through, let's say, a program, or let's say even during the testing. So flags are in fact the outputs of our ALU that we check to see if they are set or not, and based on that we kind of make a decision. Now if you look at here, you see three different flags here, right? The zero flag, the negative flag, and the carry flag. So what is the purpose of the zero flag, right? So when our ALU actually doing its addition or subtraction, sometimes we would like to know if the results of the operation is actually a zero. Therefore, we need a way to somehow detect that in the circuit. And if it's a zero, then let's say we do a specific thing. Essentially, it all goes back to the conditions that we could define in our program based on these flags. So an example would be, let's say that we are actually comparing two numbers in our ALU, and comparing A to the B number, and we would like to see if those numbers are actually equal to each other or not. So one simple thing would be actually to do a subtraction between A and B. And if the results of the subtraction is 0, that means that A and B were actually equal, right? So let's say how we could actually detect if the results of our operation is 0 on the output lines. Now, as I mentioned, those output lines go to our transceiver. However, if you look at the circuit, we are actually tapping into those output lines and connect them to another circuit on the right-hand side, which we can call it our zero flag detection circuit. So when we are actually going to have a 0 on our output, I guess when all the output lines are set to 0. So we need a circuit to detect that, and that's when we are actually tying those output lines two at a time to a NOR gate at the first stage, right? So a NOR gate will be outputting 1 only and only when both of the inputs are 0. So if we connect actually the output lines to a NOR gate two at a time, we'd be able to at least detect on those two lines if any of those are 0 or not. If both of them are 0, then we're outputting a 1 on the output of the NOR gate. So that's why we have 4 NOR gates here that covers all the 8 output lines from ALU, right? And then we also have a bunch of AND gates here, which basically combines the output of our NOR gates. So let's assume that all the lines here are 0, right? The output lines are 0, so that means that our ALU actually is outputting a 0. Now, if you look at it, if all lines are 0, the output of all of those NOR gates will be 1, right? And then we're actually combining those ones again through an AND gate here, so that we kind of, summarize all of that to a single signal, which is going to be our zero flag signal. So these AND gates here are combining the 1 and 1 outputs from the first stage, and basically if both of those lines are 1, then it's going to output a 1. The same thing happening at the bottom side. And finally, we just combine those last two signals together to another AND gate, and that means that if actually the inputs to that last AND gate is 1 on the both input lines, then the output will be 1. So in a nutshell, this circuit will be outputting 1 on the zero flag line only and when only all the lines on the input side, which are the outputs of our ALU, are set to 0. Now, there are two other flags here, which are called negative flag and carry flag. Let's first focus on the carry flag. So as you can see, the carry flag is actually connected to the carry out signal of the second chip on the left hand side. So the carry flag actually will be high, or the chip on the left hand side will be putting out a carry out signal on this pin only when the result of the operation here in our ALU is greater than 255, right? So let's say we are adding two numbers together, and if the results of that operation or that addition is greater than 255, then logically the chip on the left-hand side will be setting the carry out signal to high. And that's why we're actually connecting our carry flag directly to that carry out line. This way, we will be able to actually detect if we have a value greater than 255 in our ALU. The next flag here is a negative flag. And as you can see, it's actually connected to the most significant bit in our 8-bit binary adder. Now, the negative flag only makes sense when we are actually doing a subtraction. Or it's better to say, when we are actually dealing with signed values on the input side. So to make that clear, remember that when we are doing an addition of two positive numbers, we are not actually doing any signed numbers. We just have two positive numbers and we know that they are positive. Therefore, we are just doing an addition using two unsigned values. However, when we are doing the subtraction, since we are converting one of those values, the B side, to a negative number, then we are dealing with signed values on the input side, right? Therefore, we need to have a way to detect that actually the result of operation is a negative or a positive value, right? And that's done through a negative flag, which is connected to most significant bits. So when we are actually doing operation on assigned values, the most significant bit is actually dedicated to the sign, meaning that we only are left with 7 bits for the data, while the last bit, which is the most significant bit, is actually only showing the sign of the value. And if the value is actually a negative number, this pin will be high, showing that that's a negative. And when it's a positive number, then that pin will be low, which shows it as a positive number. So if you think about it, we are only left with 7 bits for the data, right? Therefore, our range of data, actually our range of values for the data will be from 0 to 127 or from 0 to minus 128 on the negative sides, right? So therefore, by just connecting this pin to our negative flag, or the most significant pin to negative flag, would be actually be able to detect if the results of our operation is a negative number or is a positive number. If this line is high, then that means that the result is a negative number. Otherwise, it's a positive number. Now, I know that the concept of the negative flag is a little bit confusing. However, let's go to testing part, and when we are actually testing the circuit, I could show you exactly what is happening when we actually have the subtraction and addition operation. All right, with that, I guess we are ready to go ahead and test the circuit. All right, now that we had a look at the logic behind the circuit, let's go ahead and test our ALU. So I'm gonna attach it to our Arduino shield, and as usual I'm gonna attach our LED board and connect our USB/power cable, and we are ready for the test. All right, so let's have a quick look at the sketch, and then we're going to come back to the LED board. So I guess we are ready to have a look at the sketch for testing our ALU. And now this sketch, like the other ones that we have looked so far, has a general function section that basically contains some of the functions that are responsible for resetting the Arduino board and initializing all the pins and basically setting the pins into default mode and so on. I guess we have talked about that in the previous videos. Now, the functions that are testing the ALU starts from this section. And as you can see, just like the previous sketches, we have two timers here, or variables, which basically one of them is the delay, so that we can create a delay in between the different control signals. so that we could see the LEDs. And the other one is basically just our clock length. Now, the main functions for testing our ALU actually are in our setup function here. And as you can see, I'm just initializing our serial line, and then I'm going to reset all the pins. Again, that goes back to the functions at the top. And then I have a couple of functions here, right? So the first function is actually reset registers. And this function is responsible for just clearing up both of the registers. And essentially what it does, it just write a value of 0 on the bus, and then read that value into both of the register A and B. And the reason for that is, if you think about it, the registers actually doesn't have a reset signal. So when you actually read a data into our register, it's going to be there. In normal situation, when we actually build the computer and we are running it, there is really no need to reset the registers. I mean, whenever you want to write a data, you just write it into register, and then whenever you need to read it from, you're going to read it. So here we have the function just because I'm running a couple of tests back to back, and basically when I'm writing something to the register, I want it to be clear for the next test, just so that there's no confusion on the LED board, and we actually see that all the registers are starting from 0, and that's the reason. Again, as I said, it's quite simple. It just writes 0 to both of our A and B registers. And the function is at the bottom. You could have a look at it later. The other two calls here are to two functions called ALU add and ALU subtract. So ALU add is basically the function to test the addition operation in our ALU, and ALU subtract is when we want to actually test the subtract operation. Now let's have a look at the ALU add and see what's in there. So as you can see, ALU add is actually accepting two parameters. I mean, we are sending two values to that function, and we just call them A and B, and essentially that's corresponding to the fact that the first value is going to go to A register and the second value is going to go to the B register. Now the first part of this function is really cosmetic. I mean, it's just printing one statement on the screen and just says that, okay, I'm adding A and B. So these three lines initially are just printing some statement on the screen. Now the main functions are start from here, and we are basically calling a couple of functions, right? So the first one is write to bus, and I guess I've talked about those functions in the previous video when we were actually testing our A and B registers. So I'm not going to go through them. If you haven't watched the video for A and B registers, you can go ahead and check it out. Basically, there are a couple of functions in regard to how to write to the bus and how to actually read those values into our registers. And here I'm just reusing the same functions. So the first function that I'm calling is write to the bus, which basically gets a number. Here in this case, it's our A value, and then put it on the bus. Essentially goes through bus pins one by one and set the values to either 0 or 1 until all the value, or basically the value, is actually on the bus lines. Now the next function is basically setting our register with whatever is on the bus. So this is just, saving that value which is currently on the bus into A register. Now then we're going to write the B value to the bus and repeat the same process for the B register. So this time we write the B value on the bus and then read it into our B register. So if you think about it, at this point we have both A and B registers filled with the values that we want to do an operation on it, right? However, at this point, if you think about it, the data lines are already set, and in fact our ALU has already done its operation, whether it's going to be an add or subtract. In this case, it's an addition, and therefore the results of operation from ALU is actually right now in our ALU circuit. The only thing that we need to do is basically output that result into our bus, and that's where we're actually bringing the EO line, or let's say sum out line low, that is an active low signal, so that we put whatever is in our ALU onto the bus, right? So once we did that, then we're going to read the bus. And again, this is one of those functions that I talked about that in previous video, which basically just read the bus lines one by one and get the value from the bus and print it on the screen. And finally, I have added another function here, which about reading the flags. So read from the bus is reading data from the bus lines and printing on the screen, while read flags is actually reading the value of the flags, all three flags, and print them on the screen. And finally, we just have a delay so that we actually see the LEDs in between each operation. And also finally, we're basically just set the sigma out or sum out line high, meaning that we are putting that into default and we are not actually outputting anything on the bus, right? So that's really all about ALU add. In a nutshell, we just set a value for A register, set value for a B register, and basically, because by default our ALU is doing an addition, it's going to be adding those two numbers, and then we put that number on the bus. Now, the other function is ALU subtract. And ALU subtract is quite similar. I mean, essentially we're doing the same thing, set the A value for A register, set the B value for the B register. However, if you look at this function here, you notice that before actually outputting the value on the bus, I'm setting both the EC and ES signals high, right? We talked about that when we were reviewing the circuit logic, and we said if you want to do a subtraction using our ALU, we just have to bring these two lines both high before outputting the data, and that is what is happening here, right? So this way we actually set the ALU to do a subtraction, right? The rest of the functions are the same. We're just reading a value from the bus, read the flags, and finally basically put all of those signals back to their default. Now, that's really all about it. I mean, the rest of the functions, you guys have seen them in the previous videos, and we have talked about those. So let's actually run this sketch in a couple of steps and see what will be the outputs. So let's start by testing the ALU add function. And ALU add function here is just testing the addition functionality of our ALU. So let's first comment out the subtract function, and we are just gonna start with a very simple example of adding two numbers that we could specify in this function. Now let's start with 1 and 1 and essentially see what will be the output. All right, so I'm gonna test that and I'm gonna upload it to our Arduino. All right, so as you can see, the first output is actually telling us that we are doing an operation of 1 plus 1, and this is basically the output of this section. As I said, it is more cosmetic and it's just printing out what actually we are trying to do. And then it goes through the steps and basically executes all the functions one by one. Again, the function starts by setting 1 to A register and reading it into our ALU, and also setting 1 into B register. And essentially after that, it's going to output the value inside our ALU into the bus. And finally, we're going to read the bus. So that's why if the results that we are seeing actually here on our bus line is what we expect to see, meaning that obviously 1 plus 1 will be 2. So if we see a 2, that means that we are actually reading the right value. And our ALU has basically done the addition correctly, right? So 1 plus 1 will be 2. We read a binary value of 2. And then we actually, I'm printing it several times on the screen. So this is binary, this is hex, and this is finally the decimal value. As you can see, I'm also reading the flags, right? So let's actually repeat that, and let's increase these timers to 2 seconds so that we could have a look at the LEDs. Now I'm gonna also change the values, let's say to 5 and 5, right? I'm sorry, this is ALU add function. And let's this time run that with 5 and 5 and see what actually happens on the LEDs. All right, so as you can see here at this point, everything is reset. Now we set the 5 on the bus, we read it into A register. Again, we read it into B register. And now we basically get the results of that and put it on the bus. So as you can see, 5 and 5 will be 10, and that 10 actually went onto the bus for a second, and then it disappeared. Why it disappeared? Because at the end of the function, we are actually resetting that sigma out or sum out signal to default, meaning that we are not actually outputting anything from our ALU. So if you want to actually see that, or what you could do, you could either create a longer delay timer here, or what we could do, we could just comment out that last line in our addition, which actually puts the sigma out to high, so that we can see actually the LEDs and the data basically stays there. Let's run this part again, just for the sake of example. Now, you see that the LEDs were blinking a couple of times. That's actually going to reset of the registers. But again, 5 on the A, 5 on the B, the basically output is 10, and now you can see that the EO signal is actually high, and whatever is the results of the calculation in our ALU is actually right now on the bus, which I'm reading it as 10. All right, so I guess that is pretty clear. And if you look at the screen, we see the same thing, right? So 5 plus 5, and we see the equivalent binary of 10. 0A is the hex value for 10, and basically this is the decimal value. Also, if you look at the flags, you see that all of the flags at this point are 0, which is consistent with what we see on the screen, and all the flags are actually are 0 on the LED board. All right, so I guess that's pretty clear, right? I mean, you could change the numbers here and test it with any other number that you would like. But let's move on to the ALU subtract. An ALU subtract is basically the same. It takes two numbers and do a subtract, right? So let's say that we want to do, I don't know, let's say do 8 minus 4. All right, so we set A register as 8, and we set the B register as 4. All right, so let's check that sketch and upload it and see what will happen. Now remember, at this point we are doing a subtract, right? So, all right, so we set 8 on the A register, and as you can see, we set 4 on the B register, and now we are actually enabling EC and ES. Again, that happened really quickly. So we enabled those signals, and the results were on our bus. Now again, if you wanted to actually see that for a longer time, you could just comment out the last 3 lines in the function, so that we don't actually reset those signals. All right, so let's see it. That's 8 on the A, that's 4 on the B, and now as you can see, we have EC, ES, and CO signals all high, and that basically subtract the B from A and put the value on the bus, which in this case it's a value of a 4, right? So if you look at the screen, you can see that actually that is happening here. So this time the operation is 8 minus 4, and then the result is basically 4, which is shown in binary, hex, and also in decimal. Now, at this point, I want you to just focus on the data lines, not on the flag lines, because that's going to be a little bit confusing. As you see, the carry flag is actually coming up, but we're going to talk about that in a minute. So at this point, we just want to test the basic functionality of our ALU in regard to addition and subtraction. All right, maybe we could test another thing, right? So let's test, I don't know, for example, 12 minus 10. So let's change that to 12 and set that at 10 and rerun our function. So this time, again, looking at the LEDs, now we have basically 2 as the results, which is correct, right? and basically that's it. That's really the basic subtraction functions. Now, you could actually come up with a for loop here and fit different numbers. Maybe we do it at the end of the testing that actually feed different numbers to our functions, and then it's going to be a continuous calculation of these values and printing them on the screen. So let's see how it goes. Now that we have tested the basic functionality of the addition and then subtraction functions in our ALU, now we are going to focus on the flags. Now let me just clear the screen first and maybe reduce this timers to 10 milliseconds. I guess you guys have seen the LEDs and probably you don't want to wait for a couple of seconds to see the results when you're testing the flags. So for testing the flags, we're going to go through 3 different flags. The first one is the 0 flag, and essentially with each of those flags we need to come up with some numbers here that actually causes the output of the ALU to be a value that triggers the flag basically. So let's say we want to actually have a result of 0 in our output in our ALU, right? So if you were actually doing an addition, the way to get to a 0 probably would be to just add 2 zeros together, right? So if you add 0 and 0 together, then the results will be 0, and we expect actually the flag to be set. Now let's run it and see what will happen actually. Now, yeah, as you can see, we actually have a result of a 0, and at the same time, you see that the 0 flag is actually set to 1. So that's good. Now, how about the subtraction? So if you want to actually arrive at 0 with subtraction, we probably have to set the values equal, right? Let's say we're going to do 12 and 12. So if you actually have 12 minus 12, then the results will be 0, and therefore again we're gonna have a 0 flag set through a subtraction basically operation. So let's try that. Now, as you can see, again the result is 0, and actually the 0 flag is set to 1. All right, so let's move on to next flag, which is our negative flag. Now, something important here is that the negative flag is actually only important when we are doing a subtraction. I guess I talked about that in the circuit review, and I said that basically the negative flag doesn't make sense when we are doing unsigned integers as our input values. And I'm going to show you what I mean by that. So if you go back to the circuit, if you look at here, the negative flag is actually connected to a most significant bit in our 8-bit adder, right? That means that if we are actually working on the positive numbers, any number greater than 127 is actually setting this flag to be high. And again, when we're doing addition, this flag is not important. It's not actually significant because, again, any number above 127 will actually set that flag high, right? So we're going to see that here, and I'm going to show you what I mean. So let's say that we're actually doing an addition. Let's go back to addition function, and we're going to just add 2 numbers together. So let's say we are adding 128 and let's say 10 together, right? So let's run that. And as you can see, the result is 138. However, if you look at it, you see that the negative flag is actually set to 1. It really doesn't make sense, right? We are adding 2 positive numbers to each other. However, still the negative flag is coming up as 1. So that's why when we are doing unsigned addition of positive numbers, the negative flag is insignificant. We are not going to check it. We're not going to look at it. In fact, later on, when we're developing code for our computer, we're not just looking at a negative flag. We're looking at other condition along with negative flag to make a decision. So, however, negative flag could be quite important when we are actually doing the subtraction, or we are actually doing an addition on signed values, right? So let's see what I mean by that. So if we actually comment out the addition, and now let's do a subtraction. And when we actually setting the numbers for subtraction in a way that the number that is subtracted from the A register is actually greater than A, then what will happen is that we're going to have a negative number in the output. So for example, if we say set the register A to 64 and subtract, let's say 128 from it, then the result of this operation actually will be a negative number. And that's where the negative flag actually makes sense. So let's run that. And now, as you can see, we actually subtracted 128 from 64, which should result in minus 64. Now, however, as you can see, we're actually seeing a 192 on our bus. And that's normal. I'm going to talk about that in a second. But as you can see, now we have the negative flag correctly set to 1, which means that we are actually having a negative number when we did the subtraction. So this is significant here, and this is what we will be really considering when later on we have a situation that we need to actually make a decision based on a condition. Now, why this value is 192? Well, the point is that the value that you see here on the screen is actually equal to minus 64. So if you convert this number basically back to 2's complement, you will see that this is actually equal to minus 64. However, since I'm not checking for this flag, and I'm just considering I'm reading the whole number as an 8-bit, and I'm kind of using the same function to convert it back to binary, it's actually showing up as 192. I guess that could be done by changing the code a little bit, the sketches. If you're interested in that, probably you could do it just to check this final result. And when we are doing subtraction and when we have actually a negative result, then the first or let's say the most significant bit is actually a sign bit, and the rest should be considered as a value, which in that case, if you actually do 2's complement, that is actually equal to minus 64. So that's the reason that we are not seeing that here. But again, that's a little probably a change in our sketches, and it's gonna show it correctly. Now, the last flag is actually a carry flag. Now, the carry flag is quite straightforward, right? So if we have actually a result in our ALU, which is greater than 255, we should see that the carry flag is set. So that should be easy, right? So let's set a number. Let's go back to ALU add function, and we actually add let's say 2 numbers like 128 plus let's say 192, right? So if we actually run that, you notice that now the carry flag is actually set, and that's correct because 128 plus 192 would be what? Will be 330. So let's do it actually. Let's do 128 plus 192. Yeah, it's going to be 320. And 320 is basically greater than basically 256 by 64. So that means that we're actually 64 greater than 255, or essentially if you count from 0 to 255, it's going to be the value of 256. So that means that we are actually overflowing our ALU by 64, and that's why the result that is shown on the screen is actually 64. However, the important thing is that we're actually having a carry flag set here, which is correctly set because the number is greater than 255. Now, another interesting thing that we may see here is actually when we are doing just a normal subtraction operation. So let's go back to subtraction, and let's just do 128 minus let's say 64, right? So we expect that the result is actually plus 64, right? 128 is greater than 64, so the results should be 64. However, if I run that, you will see that we actually see 64 from that subtraction operation. However, again, the carry flag is set to 1. And this is, again, one of those cases and that the carry flag is insignificant. So, meaning that it just doesn't make sense here to have a carry flag when we are actually doing a subtraction of two values. Now, if you want to really know why actually the carry flag is set here, what I recommend is that just doing these operation by hand, meaning that convert 128 to a binary, and then convert 64 to binary, and then calculate the 2's complement of this value, and then subtract those two values from each other. What you will notice is that basically there will be a carry flag at the end, which will remain beyond the original 8-bit that we have here, and that causes the carry flag to be set to 1. Now, again, this is another important point here in general in computer ALUs, that the carry flag is only significant when we are doing an addition of the unsigned integers, and the carry flag is actually ignored when we are doing a subtraction using the signed numbers. So I hope that this is clear, and these flags, when they are set, is not making you confused. This is completely normal. This is what will happen. And normally when we are actually checking those flags, we also check other conditions along with those to make a decision. I'm actually going to put a link to an online article that talks about different types of flags and where they are actually significant and where they are not. This is an interesting one, a very simple article that you could read it, and if you're like me, confused, I was initially confused about these flags, about the status of these flags in different operations. That article clearly described those situations. Now, with that, I guess we are done with those flags, and as you can see, we were able to actually check the addition, the subtraction, and a different type of flag outputs in our ALU. All right, so before wrapping up this video, let's actually do one more thing here. Let's add a for loop here so that we go through a bunch of numbers and basically do some, let's say, addition for them. So in order to do that, let's say for an integer like n equal to 0, and let's just be n less than 256, and then let's just increase or increment n by 1. All right, so n plus equals to 1, right? And then we are gonna do let's comment out this, and we're just gonna add the add function call here, with a being 0 and b be set to n. So this way we are setting the a register to 0, however the b register will be set to n, and each time we go through the loop there will be a new n, so it's going to be printed on the screen. So let's clear up the screen and let's see how this works. All right, so yeah, it looks like that we are printing all of those values in the screen from 0 to 255, and yeah, that's it. I guess we are adding 0 to all of those values. So it's interesting because if you look at the first value, which is a 0, you see that actually we have the 0 flag set, and then you're not going to see any of those flags to be set until you reach 128, which in that point you see that we actually have the negative you see that at 128 we actually have the negative flag set, but again, this is a false flag because we're just adding two positive numbers, and I guess that's about it. You could change that to actually subtract and monitor the different flags, what will happen to them. Of course, you could be always creative and change the sketches and basically come up with your own way of testing the ALU module. All right, I hope that this video has been informative and you guys were able to learn something from it. I guess we are done with our ALU system, and we're gonna build and test our memory module in the next video. So with that, see you later in video number 8.